Alright, problem 1 in the multiple choice says that a proton moves from point A, which is marked here on this diagram, following this path, and then ends at point B. How much work does the electric force do on the proton? Now the first equation, or the first principle you have to use to solve this problem, one is that the work of the electric force is going to be minus Q times the change in the potential. This is because in general in a conservative force, the work done by a conservative force is the negative of the change in potential energy. So just think about the potential energy. If it were to decrease, for example, then the kinetic would go up. That implies positive work, right? And vice versa. Okay. So in this case, we know that the proton is a positive charge, right? So this is a negative times a positive number, which is E, times that. So let me just write that. So we know it's going to be minus E times delta V. Now because the units here are given in electron volts, we know that if we measure delta V in volts and multiply it by E, we get electron volts. So the trick here is just to find the change in V. The change in V, well, the initial position is on equipotential at 150 volts, and the final position is on equipotential, which is over here measured 100 volts. So the change in V is 100 minus 150 is minus 50. So delta V is minus 50 times the minus E gives you 50 electron volts, and the correct answer here is A. One thing that might trick you up on this problem, is that this path takes them all the way up around this 50 volt sort of peak point right here, and he actually touches the 50 volt. But that's irrelevant. For the delta V, the network is only the difference between the two. Now the electric force might be doing some stuff to it up here. Probably the electric force is not doing too much work here because the electric force is pointing perpendicular largely to his path there, but the fact that he touches that is irrelevant. It's only the final minus the initial that is important. Also, you can think about it. Proton starts at 150 and ends at 10. So remember, electric field generally points downhill. So the electric field is generally kind of pointing in that direction. So were he to move straight in that direction, he'd be pushed along by the electric field, gaining speed. That implies that he must be doing positive work, and that sort of sets the sign. Alright, next question, question number 2 here. The equipotential surface in a certain region of space are planes that are parallel to the xz plane and are equally spaced, with the potential increasing in the minus y direction. An electric field vector in this region would point in which direction? This is very easy to solve if you remember the rule that the equipotentials are perpendicular to the electric field. So the electric field lines, for example, would be perpendicular. And in this case, the potential increases in the minus y direction. So if this would be the y-axis, they're getting larger as we go down, and the electric field points opposite that increase, see? So the correct answer here must be none of the above, because it must point in the positive y direction. So you can actually get this answer. If you look at the solutions, the choices here, you can answer this one pretty quickly too, because you see that if you remember, the equipotential surfaces are parallel to the xz plane. The electric field vector must be perpendicular. It has to be along the y, either up the y or down the y-axis. None of these responses has the y-axis present, so we know it must be E. Okay, we're going to skip 3 because that is a Gauss's law problem, which we did not cover, and we'll go to problem 4 here. In the figure below are shown 2 one-dimensional arrangements of charge. Each of the charges has the same magnitude. Here are the charges, 1 and 2 here and 1 and 2 there. Some are positive and some are negative. In each diagram, a point is labeled P. In which diagram would the magnitude of the force felt by a positive test charge placed at point P, here or here, be the largest? Let's just draw a simple free body diagram for each of these points. So here's point P. It's a positive test charge, so what we're going to do is think about the direction of the electric field or the electric force on that positive test charge due to each of the charges in turn. So this guy right here, since he's off to the right, his force will be to the left. That's that guy. Now this guy down here, since he's down in this direction at a 45-degree angle, he's going to pull him down, right? Because he's an opposite charge from the positive test charge, but he's a little bit farther away. And in fact, if you remember, since the electric force goes like 1 over the square of the distance, this distance is the square root of 2 times that distance, so the electric field actually, the magnitude will be 1/2, which I can draw, hopefully, a straight line in that direction, which has roughly half the magnitude of the original one. Now, in this case, let's see what we got. Let's draw this point P, and the guy on the left will execute a force on him like this. The guy beneath will push up with the same magnitude. So the net force now, let's point out, this upward vector here is due to this guy. This vector to the right is due to the one to the left, right? Because they each pushes them away. So now let's add vectors. To add this vector, there's a little square here, and that diagonal is the sum of that. Now to add this vector, I'm going to draw, let's see, I'll draw a vector about the same length as the one above it. I'll translate this vector downwards and start it down here. That looks about right. And then my sum is going to be that one. So my sum here is this vector. Now I think you'll agree that the length of this line is shorter than this line, right? In fact, you can see since this angle between the two initial vectors is greater than 90. In addition, this is shorter than that. There's two reasons why this is smaller. One, if you were to increase this angle, you would tend to start getting a shorter vector. Also, if you decrease the length of one of these vectors, you tend to get a shorter vector. So all those add up to B having the largest magnitude. You can almost guess this one, because if you think about it, this guy, he's getting pushed away, right? You got two positive ones, they're pushing him away. Those pushes kind of add up to sort of a greater push here. This one, he's being pushed away, but he's being pulled back not in the same direction, but roughly in the same direction. So here he's got a push and a pull. You might guess offhand, actually, without even doing any diagrams, you might guess that B is greater, and you would be right. Now problem 5. The figure below shows 4 one-dimensional arrangements of charge. Each of the charges has the same magnitude. Some are positive, some negative. At the point P is placed a positive test charge. What is the ranking of the magnitude of net force on a positive test charge? Okay. So what you're supposed to do here is think about how adding all these forces together would affect the net force on point P. And think about how the force varies with direction depending on which side the charge is on and its sign. For example, a plus charge on the left would push P to the right, but a minus charge on the left would pull P to the left. Also, how the force depends on distance. For example, a force here is weaker than a force here. Also, it only depends on the magnitude only depends on the distance, so not on the charge, right? So the strength of the force that this guy exerts on P is the same as the strength that this guy exerts on point P, right? So let's do some side-by-side comparisons. That's kind of the way I like to do it. First of all, I can see immediately, because the force does not, the magnitude of the force does not depend on the sign. Switching the sign here from all plus to all minus merely ends up switching the direction of the force on P. One way to think about it, you've got this guy and this guy. Well, they cancel because the force each that this point and this point exerts cancels. Likewise here and here. So if you look at these two push to the right, and these two pull to the left, but they both have the same magnitude. So we know that, for one thing, A must equal B. So that immediately eliminates some answers here. Eliminates, well, one answer. Okay, what else? The same thing we notice here. We notice that C and D, it's an identical situation. I've changed the signs. C and D are identical except for a change in sign, right? Again, by the same reasoning, all of these forces, their magnitudes are the same, but the directions are different. So going from C to D, you find out that the net force on point P, it merely changes direction and not sign. So in the first case, actually, it would be pulled to the left, and in this case, it would be pulled to the right. So that also gives us that C must equal D. And unfortunately, didn't help us much because all the answers have C equals D. But now we just have to pick one of these and compare it to one of these. So let's see which side is greater. Okay, so let's just think about this. I think let's compare, for example, A and D, because there's only one thing different. So I'm going to compare these two, right? Because there's only one thing difference here. This has all pluses here, all pluses here. This is a plus here and a minus here. There's only one difference. All I have to do is think about the effect of switching the sign of this. In this case, this guy exerts the same magnitude of force as this guy, but in opposite directions, so they cancel out, and all you have left is the force due to these. But in this case, since it's switched, this guy actually no longer cancels him. He adds to him because he pulls him to the right. So you get this plus this, but you still have this. So clearly D is bigger than A. That means CD is the largest, and that right there gives you the answer. That C is equal to D is greater than A equals B. Alright, moving right along here. Problem 6 here is a Gauss's law problem. We will not do that one. Let's move to problem 7 here. The dotted lines represent equipotential surfaces of given potential as shown below. Which set of arrows best describes the relative magnitudes and directions of the electric fields at points A and B? Now in this case, you don't have these equipotential surfaces labeled, but notice here you go 0, 10, 20, 30, 40, 50 in the same direction. This is 0, 10, 20, 30, 40, 50 in the same direction. This is a plus 50 and a plus 50. So it decreases down to 0 and then increases. Okay, so the first rule, there are two rules in relating equipotential surfaces to directions, to electric fields. One is to do with the direction. The electric field points down the down the potential. In other words, it points towards lower values of potential. And you can remember this if you use this formula, minus sign there. So if you think about this formula, the change in potential is negative E dot dr. So if your displacement is in the direction of the E field, the delta V will be negative. All right. So to get the direction, we just have to find the direction pointing downhill, basically. So this is up at 50. That's at 0. It's obviously going to the right at A. So I noticed that C does not do that. So we can eliminate it. And B, it must be going back to the left. So let's see. A does not do that. So that narrowed it down to 3 out of the 5 possibilities. Now we have to look at the magnitude. This formula, if you're using your delta R, you have to choose, often in these problems you have to choose the delta R. The delta R is up to you. And the delta R can be useful or not very useful. If we choose a delta R, for example, which is parallel to the equipotential surface, then delta V is 0, and this inner product is going to be 0 because it's perpendicular to that, so that doesn't really help us at all. But if you were to choose, say, a delta V, let's choose one over here, parallel to the electric field, perpendicular from one equipotential to the other, you would get a simple relationship. In this case, you would get your delta V equals E times D, where D now is the spacing between the equipotential surfaces, right? So that D is this spacing right here. And the signs are all right because I've got E is pointing the opposite way, so the inner product is negative, but there's a negative sign. So this is all right. And notice delta V is positive, so I'm going, the delta V here is a positive. So this formula right here is really useful to think about because now you can, this will apply for the electric field, gives you a formula for that relates the electric field magnitude to the difference in potential surfaces, and it's related to the spacing between the equipotential surfaces. And what it merely shows is that if the equipotential surfaces are equally spaced in potential, and these are, they're 10 volts apart, 10 volts, and these are 10 volts apart here, 10 volts apart here. If that's constant, then these are inversely proportional. As one gets big, the other gets small. So here we have D getting bigger than here, so that means E must be smaller here. Equipotential surfaces that are spread out indicate a weaker electric field than equipotentials close in together. So this implies that the electric field on this side should be larger than the electric field at point B. So let's look. We have B, D, and E here. So this is equal here, so that's not going to work. And here these are unequal, and this one has the A bigger than the B. So this is it. We can check with this last one. This shows a smaller electric field to a larger one, which is of course wrong, we know. So the correct answer here is D. Okay, the final problem here, multiple choice problem, number 8. An electron moves from point C to D. The electron is at rest before and after the move. How much work is done on the electron by the outside force, which is opposite to the electric force, during the move? Now, because this is a problem which involves an external or outside force, you're going to have to use the work-energy theorem. Now, the form that's useful for thinking about these problems is that the external work of the external force is equal to Q delta V plus delta K. Alright? This is like the work-energy theorem. This represents the like conservation of energy. This represents the change in kinetic energy, and this is the change in potential energy. In the absence of an external force, this would be 0. But because there is an external force, energy is being added. Because work is being performed, energy will be added, and the sum of the changes in the potential energy and the kinetic will not equal 0 in this case. Okay? All right. So we just need to go through these terms step by step and add them and get this. Now, the first statement here, it says it's at rest before and after the move, which indicates its initial and final kinetic energies are 0, which tells you that the change in kinetic energy is 0. Okay, good, that was easy. So now all we have to figure out is the change in the potential energy, replacing Q with minus E, and then delta V we have to evaluate. Delta V will be the final potential minus the initial. It moves from point C to point D. So the final is 0. The initial is 100 volts. We get minus E times minus 100 volts equals 100 electron volts. Okay, let's check our reasoning here by thinking about this. Does it make sense that the work should be positive? Okay, it kind of makes sense that this is 100 because you've seen enough of these problems and you realize that the potential difference here between D and C is 100, and the electron has a charge of E, so the fact that we get 100 electron volts in magnitude, you probably could have guessed. However, what about the sign? Well, let's think about this. So, first of all, think about the work, think about the electric force, think about the external force, what direction it has to push, and think about the sign of the work. The electric field here we can determine by what is the direction of decreasing potential. It goes from higher potential to lower potential. So the electric field points to the left. Now this is an electron, so the force on the electron actually points the opposite. There's the electric force, right? So the electric force points to the right. Now it's starting at C, going to D. Now the electric force is pushing it back towards C. So if I'm going to push it this way, if I'm going to keep it going from here to here, I'm actually pushing in the opposite direction because that electric force would accelerate it this way. So I'm pushing in the opposite direction of the electric force, and I'm actually pushing it in the direction of the motion, and hence I'm doing positive work. And sure enough, we do get a positive sign here.